as well, and my role is software.
I'm Nick, electrical engineering. I'm the team leader and also the hardware lead.
John Stefano, electrical engineering, and also hardware.
Okay, so this is just the outline of what we're going to cover in the presentation today.
So firstly, the motivation for our dual axis solar panel was that, as you can see on the graph on the right, the blue bar are the energy outputs of solar panels that only have one axis, only one direction of motion. And the green bars are dual axis solar panels that can move in 360 degrees and to capture the maximum output as well as tracking the sun. So there's a very big need for this in the market in areas where the cost to transport electricity from the power grid is higher than the cost of the solar panel.
Yep. So basically, our idea for our system design basically ran. We wanted to use the algorithm as a main sun tracking software and be able to calculate accurate position data for the sun, and that's going to be on our Raspberry Pi, and that's going to be our main kind of brain of the actual system, and that's just going to send the signals to the hardware, which is the motors and stuff, where we would have 4 linear actuators connecting to move our solar panel based on the position data we're computing.
So as Peter said, our system is comprised of 4 linear actuators that are positioned at the corners of the solar panel array, which are being powered by a 12-volt lead-acid battery, which is charged by the solar panel. So the linear actuators are driven by an 8-channel relay module, which will interface with the microcontroller, in our case the Raspberry Pi, which has the algorithm loaded onto it to track the position of the sun, which will send the instructions to the relay module, which will interface with the linear actuators to reposition the solar panel.
Okay, so this is the related theory for our sun tracking algorithm. Basically, we started by putting everything that we have in our model into vectors. So we start with a plane. We start with putting the actual solar panel in terms of a plane, as well as the base, and we have the actuators supporting the solar panel from the base as vectors as well, so that we're able to perform the equations seen on the left, and then get the key factor of our algorithm, which is the normal vector of the solar panel. This is the most important part of our algorithm because the normal vector has to be pointing directly to the sun so that we can have an angle of incidence of 0 and have the maximum output.
Okay, so this is just some of the components for the hardware, the major components being the relay board module, the voltage regulation circuit, and the solar charge controller. So the relay board is going to be what actually communicates between in the Raspberry Pi and the linear actuators, which is connected via the trigger pins of the relay board to send to the Raspberry Pi, so you can send the instruction to the trigger pins. And the voltage regulation circuit is just to break down the 12 volts from the battery to 5 volts to be used for the relay module and also the Raspberry Pi. And then the solar charge controller is used for over voltage and under voltage protection of the battery when charging it, and also for backwards current protection, so no current goes from the battery to the solar panel, causing any damage to the solar panel. So here we see the system like fully wired up with all the electrical components in that top right picture, and the bottom left of the picture is empty, and that's where the Raspberry Pi would have gone, but we couldn't do that implementation due to COVID-19. So below you see the picture there. It's just some different positions, like angles that the solar panel can go to. We did this using a substitute for the Raspberry Pi, which I had another microcontroller that I gave very basic code to just move the solar panel to test out the different positions.
Right. So our key component for our solar tracking system was the actual algorithm itself, and it just uses the basic current time function in C++ just to compute like accurate position data to find the sun in respect to the location of the solar panel using the current time. And basically, it just calculates heliocentric longitude and latitude, stores them into arrays, and does a bunch of conversions so that we're able to find like the actual position of the sun based off of the XYZ coordinates, or if we want, we can actually get spherical coordinates or polar coordinates as well. And as you can see here, I just screenshotted an output of our code because we wanted to normalize the vectors that we were getting from our algorithm because we wanted to make the data more compressed and actually have our motors able to compute based off of the changes in the outputs that we were getting. So you can just see here, we decreased the magnitude with normalization, and we were able to obtain values from -1 to 1, as you can see over there, and you can see the actual position changes according to as the algorithm is running in a loop. And also we've to make it more user friendly, we've converted the values that we had to azimuth and altitude values. And this was done using like cosine functions, inverse tangent, all that to convert actual the azimuth and altitude angles of the sun. And you can kind of get a visual representation there on the bottom left side there of the kind of angles that we were actually able to obtain to find the sun's position and the changes as well. So this is just one output of when we ran the algorithm once during the day.
So the hardware iterations on the left there, you see the picture. That's a small scale model of what we completed by the end of last semester. But we found that this design wasn't very sturdy, and it would be not wise to create this in a larger scale, like the design. So we chose a different design, which was the 4 linear actuators on the corners of the solar panel, as you see in the picture to the right there, which is the design that we've been working on for this semester and the final design for the project.
So for our software iterations, basically last semester we had a smaller scale prototype of a sun tracking panel where we kind of had a huge change with the actual software itself as well, because we were only using a system based off of photoresistor logic, and we were taking averages of 4 photoresistors that were located on each corner of our solar panel, and we had code based off of that, and we were able to make position adjustments. But now for this semester, we wanted to take it one step further, and we actually computed the actual solar location based off of our algorithm loaded onto a Raspberry Pi. But we were also able to implement this code as well into our system. We converted the Arduino code to C++ code, and we were able to have also as well on top of the algorithm a photoresistor system as well, kind of like as a failsafe.
Okay, so unit tests. We performed many unit tests for the different electrical components of the system to make sure each was working separately before we wire them all together. So as you see right there is one of the unit tests that we conducted, and the integration tests for all the electrical components when they were wired together to make sure that everything was functioning properly and communicating with each other properly. And we don't have any integration tests for the hardware and software together due to not being able to meet due to COVID-19. So we also, in turn, don't have a final acceptance test for the project either. And then here's just the corrective actions and iteration chart to show all the unit and integration tests and the failures and successes and what we did to correct each of the problems that we found.
So basically, here are just some graphical data of our algorithm results. We were just able to obtain the azimuth and altitude values of the sun, and we recorded the values throughout like 1 hour intervals of a day. And as you can see on the left, those are our recorded azimuth values throughout the day, starting from 6 o'clock, I believe, to the end of 9 o'clock. And basically, you're just supposed to see a trend of like at sunrise, the azimuth value is supposed to be around 90 degrees, and at sunset, it should be at 270. So we were able to graphically represent that. And for elevation angles or altitude angles, we also have the same amount of data where the elevation is basically the height of the sun in the sky, measured from the horizontal. So at sunrise, it's supposed to be increasing from 0, and then at the sunset, it's supposed to decrease towards 0. So, and then this is just the this is a comparison to online source that we took, basically calculating the sun's azimuth and elevation, where it actually takes this website actually takes actual longitude and latitude information, like from where you are, to calculate these position values. So it's just kind of like a comparison.
So design changes after switching to remote classes. So in terms of these hardware and software individually, they weren't impacted as much because we already had all the hardware components that we needed to finish the hardware section of the project, and also software was easily done remotely over the internet. So that those two didn't get affected as much, but the integration overall at the end did, because we weren't able to actually meet up and integrate the Raspberry Pi with the algorithm to the physical structure that we had with all of the hardware.
So as Nick said, for the project completion, we had completed the hardware and software modules separately, but we weren't able to finalize the integration tests because the modules were in separate locations, and due to social distancing, we were unable to complete this integration. For the future works of this project, if we had more time and in a setting where we could integrate our modules, we would also have liked to include a smartphone application that would interact with the solar panel and would give the user some control over the solar panel, such as multiple functions, as to shut it down, as to view the energy output, the efficiency percentage that it's getting, which way the solar panel is facing. So we also would have wanted to include this if we had more time.
So just to break down the cost, we obviously tried to keep everything as tight financially as possible that we could. Everything between the capacitor, wood, springs, metal, screws, all the way down to our actual relay modules and motors. So as a total, we ended up spending $305.70. The only thing that we didn't include in the actual chart was the Raspberry Pi, which Peter owns himself, and the microcontroller, which Nick had. But at the end of the day, we tried to keep it as tight that we possibly could.
And here's just the demonstration video that I put together using the substitute microcontroller that I had. Just to show the way that it can move, like each actuator can move individually to reposition the solar panels in different angles. You can see here how the two actuators there on the left go up to move it facing that way, and then also go down to reposition it.
So just a couple things to keep in mind: the code standards and constraints. In each state, when it comes to building and designing these solar panels, we have to follow a set of codes and standards that are set specific for each location, usually broken down by different states. So these differences based on income, geography, green-friendly laws, anything that differentiates them. And the code has to be followed by the designers and the builders of the solar panels. So a couple different setbacks or regulations that have to be put into play would be like permitted obstructions, things like that. and compliances, for example, with the fire department, FDNY, or DEP, the Department of Environmental Protection, and the DOT, which is the Department of Transportation. So for ethics and analysis, we have the IEEE Code of Ethics, which is the recognition of the importance of our technologies in affecting the quality of life throughout the world and accepting personal obligations in our professions. A list of 10, which as a group we decided that numbers 5 and 6 would more pertain to our project more significantly, which basically just improving understanding by individuals in society, the capabilities of societal implications, and emerging technologies. For 6, just to quickly refresh, just to maintain and improve technical competence and to undertake technological tasks for others.
And as you can see, this is the timeline on the right. And so we have the software configuration, hardware devices, the software implication, and the application development. So the reason that one of the reasons that I forgot to mention before, the reason that the software configuration is not as hefty as a timeline that you would assume is because a little bit of the theory that we obtained for our software algorithm was obtained from a previous group called Project Sunshine that also worked on a different style of dual axis solar panels, but they had a stepper algorithm instead of a actuator algorithm. And there's the timeline. Our workload by member is on the bottom, and the Gantt chart for the workload is on the left.
And here are just the references that we used for this project. So, any questions?
Okay.
Okay, thank you.
Thank you, guys.
Hello?
Thank
Thank
you.
you.